All right, welcome to The Explainer. Today, we're going to decode a secret language. It's literally all around you, hidden in plain sight, on ingredient lists and lab reports. We are talking about chemical nomenclature.
Think about it. You run into dozens of chemical compounds every single day, from the salt on your food to the bleach under your sink. But have you ever just stopped and wondered, hey, how do they actually get their names?
I mean, take something simple like table salt or baking soda. They've got these official names that, can seem a little complicated. But here's the thing, they are not random at all. There's actually a surprisingly logical system behind it all, one that tells you exactly what's inside.
So how do we make that jump? From a formula like NaCl to a name like sodium chloride. Well, it all kicks off with a system called nomenclature. And really, this is just the official rulebook for naming chemical compounds.
Yeah, think of it just like the grammar for the language of chemistry. It's this universal set of rules, right? It makes sure that a chemist in Tokyo and another one in Toronto are talking about the exact same thing. It's all about clarity and, honestly, safety.
Okay, so let's get into the nitty-gritty. The very first step in naming any compound is asking one super important question. And the answer to this question splits our path in two.
Right. This one decision tells you exactly which set of grammar rules to follow. And the best part? The clue is hiding in plain sight, right at the beginning of the chemical formula.
And it really is this simple. If the formula kicks off with a metal, you've got an ionic compound. If it's made up of only nonmetals, then it's what we call a covalent or molecular compound. So let's go down that ionic path first. All right. Naming the simple ionic compounds, the ones with just a metal and a nonmetal, is actually pretty straightforward. It's really just a two-step process. So here's what you do. First, you just state the name of the metal. That's the positively charged part, the cation. Then for the nonmetal, the negatively charged anion, you just chop off its ending and swap it with "-ide". That's it.
So for instance, the element chlorine, it becomes the ion chloride. And oxygen, that becomes oxide. Let's see how this plays out with a couple more examples.
Okay, so NaCl becomes sodium chloride. Simple enough. KBr is potassium bromide. And CaI2 is calcium iodide. You see that pattern, right? It's so consistent, and that's what makes the system so powerful. It's all about clear communication.
But, just when you think you've got it down, chemistry loves to throw a curveball. What happens when a metal can have more than one possible charge? This is super common for what we call the transition metals, that big block of elements right in the middle of the periodic table.
And listen, this is not just some little detail for a chemistry quiz. Getting a chemical's name wrong, having any ambiguity, can have some really serious real-world consequences. We're talking life or death in some cases.
And that brings us to a really famous case, one you might have even seen a movie about. It involves the legal clerk Erin Brockovich. Her investigation uncovered how one specific type of chromium compound, used by Pacific Gas and Electric, was contaminating the groundwater in Hinckley, California, and it was being linked to some very serious illnesses in the community.
Right, so that lawsuit against PG&E, it led to that massive settlement you see here. And it all boiled down to the critical chemical difference between two forms of the same exact element, chromium. Okay, so here's the crucial point. You've got chromium-3, or Cr3. This stuff is actually an ingredient in a lot of vitamin supplements, and it has pretty low toxicity. But then, you've got chromium-6, or Cr6. This form is highly toxic. It can cause severe damage to the body, and the name has to show that difference.
So how do we solve this problem? Simple. We use Roman numerals in parentheses right after the metal's name to nail down its exact charge. So FeCl2 is, without a doubt, iron 2 chloride, and FeCl3 is iron 3 chloride. See? No confusion, zero ambiguity.
Okay, so that's how we handle ionic compounds. But what about that other path we talked about at the beginning? The one for covalent compounds, the ones made of only nonmetals. Well, it's a different type of compound, so, you guessed it, it needs a different set of naming rules. With these compounds, we have to be super explicit about how many atoms of each element are in there. And this is the perfect example of why. Look at CO and CO2. They're both made of carbon and oxygen, right? But they are completely different substances. We can't just call them both carbon oxide. That would be a disaster. So, to fix this, we use a really elegant system of Greek prefixes. And these prefixes tell you exactly how many atoms of each element are in the molecule. It's mono for 1, di for 2, tri for 3, and so on. Pretty straightforward.
And what this system gives us is incredibly clear, precise names. So SO2 becomes sulfur dioxide, N2O4 is dinitrogen tetroxide, and SF6, that's sulfur hexafluoride. It leaves absolutely no room for confusion at all.
All right, to wrap things up, let's just briefly touch on one more special case, kind of like an advanced topic. There's this really important class of compounds called acids, and because they're so unique, they get their own special naming rules.
For the simple acids, the ones made of just hydrogen and one other nonmetal, we use the prefix hydro and we change the ending to ic. So, for example, you take the gas hydrogen chloride, HCl. When you dissolve that in water, it becomes the stuff you've definitely heard of, hydrochloric acid.
And there you go. You've just learned the basic grammar of chemistry's secret language. So seriously, the next time you pick up a bottle of cleaner or you're just glancing at an ingredients list, you'll actually be able to translate it. So the real question is, what are you going to discover hiding in plain sight?